Hello everyone, welcome back to another geostatistics lecture video. And in this video I want to talk about building the neighborhood matrix in R. And we're going to be using the Georgia dataset from GIS tools, so that's one of the packages. The other package that's going to be doing all of the work here is the SPDEP or SPDEP, however you want to pronounce it. This package is going to handle all of the heavy lifting of creating the matrices and all of that. I'm including the SP package just because we're going to be working with the spatial polygons data frames, and it's nice to just have that in there in case we need to call a function. So these are the only three packages that we're going to need for these activities. So I'm going to go ahead and I'm going to run this code chunk to give us all of our packages. Okay, so now that we have all of our packages installed, we can go ahead and work on our neighborhood matrix. So the neighborhood matrix is going to come in two steps. The first is going to be generating connectivity, and then going to be converting to the matrix. Right? And so the first function that we're going to have to consider is this function called poly2nb. I'm going to make my thing appear here. Before we do anything though, we need to bring in our data. And again, we're going to use the Georgia data from the GIS tools package. So now we have access to the Georgia polygons. And to be clear here, what we're going to be using in for these videos, if we go into the data set, we're going to be using this %rural variable. So this is a floating point or double that is the percentage of the population of that particular county that is considered rural. So what we're going to do is we're going to go in here and we're going to look at two different functions. The connectivity function is going to be brought in using SPDEP poly to NB. So polygon to a neighborhood matrix. And if we look at the help description here, you'll see here that we have two parameters that we really need to worry about. The first is this PL. These are the polygons that you're going to use. And then the other is this queen. So if you remember back to our discussion on the different types of adjacency, right, we had rook, queen, and then if you wanted, you could have lagged, but we're not going to worry about lagged. But you do have to worry about queen. So by default, poly2nb uses the queen's case, where it includes polygons that share just a vertice. So what we're going to do is we're going to, using our Georgia data set, we're going to generate our first set of neighborhood matrices, and I'm actually going to do both just to show you the differences as we go along and how they look. So what I want to do first is we're going to set up our rook NB for our rook neighborhood data structure, and we're going to call in that poly SPDEP. We're going to call in our poly to NB. And again, right, we need our PL, which is the polygons that we're bringing in, and this is going to be our Georgia. Right. Okay. And then because we're doing the rook's case, we need to set queen equal to false. Right, so this is going to create a rook's set of neighbors. We can also do, again, the queen neighbors, which would be SPDEP, poly to NB. We're going to use the same polygons, so PL equals Georgia. Right, that stays the same. But in this case, even though this is not strictly necessary, I always like to specify any parameters that I know I need to. And I'm specifying queen here, so there is no ambiguity that this is going to be a queens-based neighborhood matrix. So hopefully that makes sense. The next thing we can do is we can actually visualize the weights matrix by using a function. We can visualize the neighbors by using a function called nb2 lines, which actually, let's go down here again, question mark nb2 lines. Right, so this nb2 lines has a nb object, so this is the neighborhood object that we just created, coordinates for the where to put them, and this project for string, which is going to be the projection. So what we can do is we can call Rook Lines. We can call spdep : and again it's going to be nb2 lines. And this is going to take in those parameters. NB, this is going to be our rook underscore NB, right? That's our neighborhood thing. We also need the chords. So the chords is going to be coming from the Georgia data set using the coordinate, using the sp : coordinates function. This takes in an object, and that object is going to be our Georgia data set. Right, this is going to get the centroid of the Georgia of each polygon. And then finally, we have our proj for string, which is going to be equal to Georgia at proj for string. Right, this is just projecting it into the right projection. This last one probably isn't completely necessary, but it's good to specify. Right, and now we can copy. I'm going to copy this. And I'm going to just quickly do queen lines. And I'm going to switch rook NB to queen NB. And everything else is going to stay the same. If I run that. Okay. So what I want to do really quickly, just to show you the differences, I want to plot both of these. I'm going to use the generic plot because it's a little easier to deal with. We're going to do rook. Let's do queen lines on bottom. And we're going to set the color equal to, let's do blue. Let's actually run this. And then, so if we scroll a little bit, you can see those. And then what I want to do is I want to plot rook underscore lines, set that equal to red. And then I want to do add equals true so that it gets added to the plot. What did I do? Oh, I have to call them at the same time. That would be what I did wrong. There we go. So you can see where the blue lines show through and the red lines don't. Those are the differences in connectivity between the queen and the rook. So each one of those crossing lines means that there were two polygons that shared only a single vertex rather than an edge. Okay, so the last step in creating a weights matrix, or creating the spatial weights matrix, is going to be converting from the neighborhoods to the actual weights. And that is done through a function called nb2listw. Right? spdep again, nb2listw. So this converts the neighborhood list to a spatial weights matrix. So you can see here that it takes in neighbors and then this style here. So if we scroll down to style, it'll tell you what the different style options do. Basically, we almost always want W. We want to row standardize the matrix. Which is actually the default. Okay, so let's go ahead and let's do continue on with our idea here. We do rook underscore lines equal, sorry, this will be rook underscore spatial weights matrix is going to be equal to spdep colon colon, and then we're going to call again that nb2 line, or sorry, nb2 list w, because again this is going to convert our neighborhood list to a spatial weights matrix, and it requires the neighbors parameter to be our spatial weight, or sorry, not our spatial weights, to be our neighborhood matrix. So this is going to be our rook underscore nb, and that's all we really need to pass in for now. Right? If we run that, we now have a spatial weights matrix. We can also do our queen underscore spatial weights matrix equal to spdep colon colon nb2 list w, and then in this case neighbors is going to be queen underscore nb. Okay, so hopefully that made sense. Hopefully when we plotted it, you were able to see the difference between rook and queen in sort of a more visual way. Again, the concept here is you generate your connectivities in the first step, visualize them if you'd like, and then convert them to the actual weights matrix. So hopefully that makes sense. And as always, please reach out. Thank you.